I would like to do, since it's been such a long time, I want to spend about 15 minutes reviewing the material that we've forgotten over the past 3 weeks, right? And then once we get past that, we'll introduce some new material. We're going to be looking at some really interesting stuff today. We're going to be looking at an introduction to probability and how it impacts on statistics. And we're going to be looking at diagnostic tests. How many of you guys, when you go to a doctor and he does diagnostic tests, ask for the positive predictive value of that test? How many of you guys know what the positive predictive value is? Okay, well, you're going to know by the end of the day today, you're going to know what the positive predictive value. You're going to know a lot more about tests. So you're going to know about sensitivity, specificity, how to calculate those, how to determine them for a test, and how they impact on how good a diagnostic test is. And it's got a lot to do with all of this eventually winding up with positive predictive value. In other words, if you get a positive result on a test, how likely it is that you actually have the condition that the test is predicting that you have, which is really important, right? So if you go to a certain kind, if you go to a doctor and you get a certain kind of screening, and the doctor says, well, you tested positive, I'm going to send you to a specialist. You want to know, well, now that I've tested positive, does that absolutely mean I have the disease? Or what's the probability that I have the disease given that I've tested positive? So that's important, right? Because how you react to a positive test could be expensive, could be invasive, could be dangerous even, right? So we're going to learn about that stuff. For starters, though, I just want to go back here and look at, just want to make sure we're okay online. I'm going to mute everybody so we don't have any background noise. Okay, if you have a microphone, please keep it turned off. Otherwise, we'll get the website. I'll put it up here right now. I'll type it in rather than. It's GoToMeetMe /GoToMeetMe.com/Tony DeVito. I should give it a better name, a little bit more generic. Let me just open up a Word document here. Okay. Now blow that up real big. Make it a little bit smaller so I can fit it in. Still not working there. Okay. Actually, better way to do this, go to 20% and go to a smaller font size. There we go. Okay. If you want to log in on your own computers, you can do that. You'll see everything that you, oh, I'm not logged in here, am I? You guys got to tell me this. It's behind me. You can't see it. Right. And they're going to make this. Okay, if you go to that site, it'll ask you to run a plugin. Tell it to go ahead and run it, and you'll see what's behind me. You'll see right on your own computers. That way, if you're in a bad spot, you can't see this very well. It's also not very bright, especially with the lights on in the room. You'll be able to just look straight at your monitor as I'm talking and literally see what's on the board behind me as well. Anyway, okay, so I'll get this out of the way. And I'll move this out of the way. Okay. How many of you guys have completed assignment 1? Okay, any problems with assignment 1? How about any issues with cutting and pasting the tables into a Word document?
Yeah, I had emailed It was because I didn't have Word downloaded onto my computer. It was just through the internet.
Oh, I see.
Once I did that, I
Okay, good. All right. I personally have an issue with it. I've had various iterations of Word over, updating and reinstalled over a period of time, and my Word and SPSS have an issue with cutting and pasting. So you may see me do some extraordinary things to get tables or charts into my Word documents or whatever text editor I'm using. Okay, so let's take a look at this. I'm going to open up an Excel file called Descriptive. It's on Blackboard. Descriptive Statistics, Excel, Descriptive Statistics, Exercise 1. Okay, and this is just directly what you did on homework. Again, I just want to go over this in order to make sure that we're familiar with this. Now, you may remember that we went through an exercise where we actually derived how the sum of squares is calculated, right? We took a sample, a sample of 18 people. This might be, for instance, blood pressures, for instance. We took a sample, we took the average of that sample. We found the mean. Function we used was equals average in Excel. We then took that mean and we subtracted each individual value from that mean. In other words, the value X, which is each one of these values, minus the average X bar. I have it notated here as X bar because it's easier than putting an X with a bar on top, right? That's the average. I would take each individual value, subtract it from the mean, and that would give me this next column, X minus X bar. That's the difference between each value in the mean. So the bigger that difference is, the more variability that there is in that data, the further spread out it is. Well, I can't just add them all together because what happens is I wind up getting 0 because half the value is below the mean, half the value is above. So half of them are negative, half of them are positive, and they cancel out. So one of the ways to get around that with negative numbers is to square a number. Negative times a negative turns out to be a positive, as does a positive times a positive. So we put that into X minus X bar squared. And we added all those together, and we got something called the sum of the squares of the differences, commonly called sum of squares. Okay, that number is important because that number leads us, that number, number one, gives us an idea of what the variability is like. Since it's dependent on the size of the differences, and you square it, it even amplifies the size, so you can get a view of how variable the data is, how far away the values are from the mean, how spread out they are. However, okay, so in order to look at that from the perspective of an individual value, we divided that by the sample size. So we get an average of the sum of squares, right? There's a name for that. It's called a variance. Now you'll notice here that I say it's the sum of squares divided by n minus 1, the sample size minus 1, 17 instead of 18. We do that for samples. If we're doing it with a population, the variance is equal to just all of the different sum of squares divided by the population size, just n. For a sample, we use n minus 1. There's technical reasons for that. We don't have to worry about that right now. Maybe later on, if we have more time, we'll worry about that in terms of how we're going to, what the reasoning behind that is. For starters, keep in mind that's also sometimes called degrees of freedom, right? So if you have one value, if you only take one person's weight or blood pressure, all you know is that person's value. You have no idea what the variability is. So that's just one person. So you really don't have a capability of understanding what the variability is. So you only have that one value. So you really have no freedom to see what the range, what the variability is. If you have two values, well, now you have a choice. You have one choice that you can make, one or the other, and then 3 or 4. So that's where kind of that idea of degrees of freedom comes from. So if you have a sample of 8, you have 7 degrees of freedom. If you have a sample of 100, you have 99 degrees of freedom. So, but we're not worried about that right now. We just want to understand that we use n minus 1, and that sometimes that's called the degrees of freedom. Now, because the variance is multiplied, because it's an average sum of squares, We want to bring it back down into the range of numbers, the numbers themselves. So we take the variance, we find the square root of it, and we have something now called the standard deviation. That's going to become real important to us, right? So the mean is our main measure of central tendency in this sample, right? Where's the middle? Okay, and the standard deviation is going to be eventually our main measure of what the variability is, how spread out it is, right? It's kind of an artificial number right now, but it really does become important later on. Another way that we measure variability is to just simply look at the minimum and the maximum and the difference between the two, and that gives us something called a range. Again, a measure of the variability. Another way of measuring variability is to look at percentiles, right? So in other words, you guys, many of you guys took the GREs or about to take the GREs at some point, and in addition to your score, they probably report a percentile. And that tells you if you're the 75th percentile, that means, or you're in the 25th percentile, let's say, that means 25% of the people scored better than you, but 75% of the people scored worse than you. It's the percentage where you are in terms of the entire sample or population, whichever one it happens to be. Okay, there's a special view of that we're interested in. We're interested in where's the middle 50%? What range is the middle 50% of the people, these people's blood pressures? Where is that? We call that the interquartile range. And the middle 50% is from the 25th percentile to the 75th percentile. Well, now we did this the hard way, right? But of course, we know in the homework that we instead use built-in functions in Excel, right? So for instance, when we wanted to calculate the mean, we said equals the average, parentheses, of all of these values, of all the values for the individual X's, all the blood pressures. And the average came out to be pretty close to 100. When we wanted to calculate the standard deviation, we use a function in Excel called standard deviation, STDEV, parentheses. And as soon as I hit in at the open parentheses, if I did it right, it pops up and asks me to tell it, to give it what information it needs to calculate standard deviation, which is the value of all the numbers that are included in that range. Notice I click in and drag, so it automatically fills in the cell numbers for me. I know I'm going fast, but I'm doing it on purpose because I just want to do this as a review. How are you guys doing online, by the way? Can you hear me and see my screen? And are you keeping up?
Yes. Yes, we can see.
I
Thank
have you
you.
guys all muted because otherwise there'd be a cacophony and noise on the recording. So I can't afford to have, when there's a more than just a couple of people, I can't afford to have it. So type into the chat box for me. Type faster. You're holding us up. You guys can see me, right? You guys online? Are you guys awake? Maybe it's just you guys that are logged on. Maybe there aren't people on. Ah, finally. Okay, good. We got somebody to answer that. Okay, so you guys that are just walking in, I'm kind of doing a review of what we were doing for the first couple of weeks because it's been so long. Don't worry about it. It's being recorded. You'll be able to see it later on. Okay, so at any rate, if I wanted to calculate the variance, it's going to be equal to VAR parentheses. Okay, and again, ask me for that range of numbers, A2 through A19, 18 values. And what can you tell me about that variance and standard deviation? It's the square root of the variance and standard deviation, right? I can confirm that. There's a function square root, SQRT parentheses. I'm going to take the square root of 52, and it comes out to the same value that I got using standard deviation. Okay, so now, what other measures do I have? I have the mode, equals mode, parentheses, and there is a function called mode. And what is the mode? That's the most frequently occurring value, right? That's kind of a measure of central tendency also. The mode is 104. Well, the mode is 104 because there's only there are 304s. right? Well, there might have been some other values that there were three of also. SPSS, Excel, most of these programs only report the lowest value for the mode. So if there's more than one mode, it won't show you. It'll only show you the lowest value. Maybe there's 304s. Maybe there's also 301s as well. Maybe there's two modes, right? Maybe there's three modes, right? But I wouldn't worry about that too much because mode isn't one of those statistics that we use usefully that often. So it's of some interest. In fact, sometimes the mode is more interesting when you look at a categorical variable than when if you look at a numerical variable. Because in a categorical variable, if you are looking at, say, 7 ethnicities in terms of mortality rates or something like that, what you're going to be interested in, you might be interested in which ethnicity had the highest mortality rate, right? So mode might be even more interesting for a categorical variable. So if you run into that, multiple modes, don't worry about it. SPSS at least gives you a little asterisk there that says there's multiple modes if there are. Excel doesn't even warn you about that, I don't believe. Okay, so now what do we have in terms, what else do we have in terms of measuring the center of a distribution? Well, you also have the median. Right? Median is the middle value equals parentheses, and it's going to ask me for that range of numbers again. So the middle value is 100. What is the middle value? Is there another way for me to describe the middle value? Half the people are above you, half the people are, remember what I told you about that, your score in on the GREs, right? 25 percentile. So the median, half the people are above, half the people are below. So what does that make that? Makes it the 50th percentile, right? Okay, so that's also the 50th percentile. So let's look at the minimum and the maximum. Equals minimum, MIN, and maximum equals MAX, parentheses. Again, I'm doing this really quickly on purpose. And the range is the difference between the maximum and the minimum, equals 114 minus 88. So the range is 26 millimeters of mercury, if these are blood pressures. Okay, so now what's another measure of variability? Well, that was our percentiles that we were talking about. So really what I'm interested in interquartile range. Kind of the range, except instead of going from the lowest number to the highest number, it's looking at the middle 50%. So we want the 25th percentile and 75th percentile. There's a function in Excel, equals percentile, parentheses. Notice there are newer versions of this percentile that you would use in specific applications. I'm just showing you the simplest one so you don't have to be concerned. You can just go ahead and use percentile. Percentile, and it wants to know the array, the list of numbers, comma, and it wants to know K. K is the percentile that you're interested in. It's expressed as a decimal point. 0.75 is the 75th percentile. And I'm going to hit enter. And 75th percentile is 104. Notice it's the opposite direction that you would, the GREs, usually 10th percentile, they're looking at the highest scores. This one, you're just looking at where it is in that list of numbers. What about 25th percentile? Well, same thing. Except that this time, instead of 8, we're going to use A2 through A19. I'm typing it in this time so you can see you can do that as well. And 0.25 to 25th percentile. And the difference between the two is equal to the 75th percentile minus the 25th percentile. And that's 9.5. So there's only, look at the difference in the range and the difference in the interquartile range. A lot of those, most of the people in this group are clustered around the middle, which is usually what you see in a normal distribution. More people around the middle, fewer and fewer people spread out far and wide. I think they're, well, okay, I'm going to leave that at that. Now, you may notice when you use SPSS, how many of you guys notice this, that you got a different value for the interquartile range in SPSS? That's because SPSS uses a different mechanism for calculating the interquartile range. For example, one of the ways that Excel might be calculating the interquartile range is by looking at all of these numbers and figuring out where the middle is, the 50th percentile, which is the median, right, 100. And then it may be saying to itself, okay, well, the 25th percentile is the value that's between the lowest number, which is 88, and 100, and taking that number as the 25th percentile, and doing the same thing between the median and the biggest number, finding the middle number in there. In other words, breaking it up into quarters, right? That may be the way that Excel is doing it. SPSS may be taking these numbers, creating a normal distribution. In other words, taking the mean and the standard deviation, assuming the distribution is normal, and looking at where, if it's a normal distribution, instead of just looking at the sample, looking at the overall population, and trying to predict where in the population that this sample represents, you would have the 25th percentile and 75th percentile, and they get a slightly different number for the interquartile range. That may be the way that SPSS is doing it. In fact, SPSS has buried in it ways for you to tell it anywhere from, I think, 4 or 5 different ways to calculate percentiles and interquartile range. You guys don't have to worry about that. In any case where they're different or there's some ambiguity, I'll make sure that both answers are judged correctly. So for our purposes, you could use either way of doing it. A real statistician would probably never use Excel or this kind of stuff, except maybe to do some quick calculations and stuff like that. They would rely more on a program that's specifically designed for statistical calculations. Okay, so I'm thinking ahead. That's why I'm hesitating a little bit. Okay, so now let's take these same numbers and look at them in SPSS. Okay, import them into SPSS. There's another file. Actually, I'm going to do this a little bit. There's another file there, which is Excel to SPSS, which is just another Excel file, except that instead of having all of this detritus around it, it just has, I'm going to blow this up, it just has the numbers in it. Okay, you know what I'm going to do up here? I'm going to put BP for blood pressure, and then I'm going to go in here and paste in these numbers, those 18 numbers that we're interested in. And I'm going to save this file. I think there's a file on there. As I said, there's a file, Excel to SPSS, .excel, which I believe has the same thing in it, but I'm gonna do it anyway. Okay, I'm gonna call this import demonstration demo and save it to my desktop. Okay, so now here's my numbers. The top row is my variable name, blood pressure, right? So I want to bring these into SPSS. So the first thing I need to do, I've saved the file to my desktop. First thing I need to do is close the file. SPSS will not import files from another program that are open in that program, right? Doesn't want them to get modified. So I'm going to start SPSS after I close that file. And once SPSS starts up, and I think I can show you here somewhere. See if I can get it before it. You see it there in the right, in that corner there? Oh my goodness. Get this out of the way. Okay. You can't, it's too far off onto the right-hand side. You can't see it. But here, the file is there. Trust me. Yeah, let me see if I can't get you to see it. See it there? There it is. Right, files on the desktop. Okay, so this opening window comes up. A lot of people just say, don't show this dialog in the future. I leave it here in case students have it set up that way, but I'm going to just brush it off, let it go away. I'm going to go up to File. SPSS is still open. You can see the drop menus at the top. I'm going to say File, Open, Data. I'm going to navigate to my desktop. And my desktop. And on my desktop, I didn't get to my desktop yet. There we go. Okay, there's my desktop. And I'm going to go to this file, and I don't see the file. Okay, by now you guys should know why I'm not seeing the file. right? It's an Excel file. An SPSS right now is only looking for .sav for SPSS files, right? So I have to let it know that the file I want to open is an Excel file. So I can click down on that, and I get a drop down that allows me to choose Excel files. And now I should see any Excel files that are on my desktop. There's several there, including the one we just created, import demo Excel. So I'm going to open that up. I'm going to double click it or click open. It's going to open, be imported into SPSS, but first it's going to ask me some questions about it. First, it's going to tell me what it sees is one worksheet in Excel, and it sees values from A1 to A19. That sounds right to me, right? Remember, it's 18 people, and the top row is the variable name, blood pressure, BP. Okay, and it says, checked off, read variable names from the first row of data. That's important because if you look in here, it recognizes that that first row is not a value in the data. It's actually just a variable name, so we'll put it at the top. Okay, and then it started with the first number that was present. If I turn that off, it's going to try and give it a fake variable name, D1, and try and include that in the data. So that has, if that's the case, I need to check that off. If you don't have a variable name in the top row and it's all data, you want to make sure that's unclicked because otherwise you'll lose that first row of data. Okay. So I'm going to click OK. There's a few other things there, but I'm going to go ahead and click OK. And it's going to import that into SPSS. It's going to open an SPS data file, and there's my SPS data file. In this view, called the data view, I can see the data and the variable at the top, right? If I click to my variable view, I get a single row because there's only one column, only one variable that I'm dealing with. And I can go through here and specify certain things that are relevant to this particular variable. For instance, instead of BP, I can go in here to label and put in blood pressure. So that way, instead of my tables and charts saying the variable name BP, which is kind of an abbreviation, it will actually say blood pressure, be a little bit more descriptive. Okay, I can go over here to the end and tell it whether it's a numerical variable or categorical variable. If I click down on this, I have three choices in SPSS. Scalar, which is a numerical variable. Okay, again, this is a little bit of review, right? We talked about variable types. It's a numerical variable. It's a number. It's on a scale. Could be a nominal variable. A nominal variable is a name, gender, ethnicity, so on and so forth. Or it could be an ordinal variable. An ordinal variable is something that implies its categories, but it implies degree, like a relative degree, like good, better, best, or something like that, right? So in other words, one of them might be pain level, right? Low, medium, high. Those are categories, right? That's a word. Low, medium, high. Those are words. But those words imply medium is worse than low, high is worse than medium, and low, and so on. Okay? You can't quantify them like a number, but it's different than an ordinary categorical variable or nominal variable. So we know this is scalar, so that's right. So I'm going to go back to the data view. And now, in order to do my analysis, I can go here to analyze. And I'm interested in descriptive statistics. That's what these statistics are. Go over here to descriptives and tell it that the variable I want to work with, remember there could be many variables here, not just one. So pick out the one I want to work with, move it into variables. I can go into options, and I can ask it to find the variance, the range, so on and so forth. I don't see percentiles in here or interquartile range. So I'm going to click continue. I'm going to say, okay, a window comes up and I get results. I get the range, minimum and maximum. I get the mean, standard deviation, variance. These numbers are familiar, right? They're exactly the same numbers we got before. I got them in an instant this time. Okay, so now what else can I do here? What about the statistics that I'm missing? Well, I can go into analyze again, go into descriptive statistics, go into explore. Next step, it's still into descriptive statistics. I'm going to move this into the dependence list. In other words, tell it what variable I want to work with. And then I can click on statistics just to make sure that it's calculating my confidence interval. And look, there's a little checkbox for percentiles as well. So I'm going to click OK. And now my output window is going to come up again. Remember, You got two separate windows for SPSS open now. You have a data window, which has two views, variable and data, and you have an output window where all of your results are going. So here's our output window, and now we have more data than we had before. We have mean, median, variance, minimum, maximum, range, interquartile range. Notice it's calculated a bit differently than what we did in Excel. I'm glad I warned you about that. And here's percentiles for 5 percentile, 25th percentile, 50th percentile. Notice 50th percentile, again, it's the median, 75th percentile, and so on and so forth. So, and we also get something interesting. We get a box plot. And the box plot is interesting because it really explains graphically a lot of information about this variable. Here's a little feather down here. We call that a feather. That's the lowest value. The feather at the top is the highest value. The box represents, the bottom of the box represents the 25th percentile, and the top of the box represents the 75th percentile. So this blue area is our interquartile range. And this black line, this dark black line here, what do you think that is? What's that? The median. It's the median, exactly. It's not the mean, it's the median value, right? That's our 50th percentile. Good, exactly right. So we were able to get all this information. You could also, if you wanted to, go into descriptive statistics and frequencies. And a lot of times we use this for creating charts for nominal, numerical variables. You can also go in here and hit statistics and get a variety of statistics from this as well. Okay, cut points for 10 equal groups, the percentiles. Okay, I don't need to do that. Mean, median, mode. I'll just hit continue here. So you can see that you can get the percentiles out of there as well. There's the percentiles. So on and so forth. There's our 50th percentile is the same. Okay, so that's just some interesting. Only other thing that's interesting that might be that I want to emphasize. Also, I'm gonna use Open Office because I'm gonna roll the dice here and see if it works with this instead of Word. But remember, I told you my version of Word is having some difficulty with this stuff. I can go in here, and this is like a ticker tape. All of the analyses that I've done are on this sheet. So I'm gonna go here, click one of these tables. I'll click that's a little bit neater one. And it's, you can see it's selected because there's a box around it. I'm gonna say copy. Then I'm going to go into my text processing my word processing document and say paste. And there's my table. Unfortunately, it pasted it as a plain text file. Hopefully yours does better than mine does. In fact, if it's working properly, you can go beyond paste and go to paste special. And you should see mine says the only selection I have is unformatted text. That's a problem of my operating system, okay, which I've been having problems fixing. But that says if it's working properly, you should have several options here, including formatted text and including a picture, like a JPEG or some other form of picture, where you could actually paste that in as a picture of the table rather than something with numbers on it. The downside of that is pasting it in as a picture, if you have that option. Downside of that is that once it's in the document, Word document, or the text processing, or the other editing document, you won't be able to make any changes to the formatting or the numbers or anything like that. The good part of it is since it's in there as a picture, it's a lot easier to make bigger or smaller or move around. To reformat. Okay, so you can do the same thing with the pictures. I'm going to predict that this is not going to work. I'm going to hit Control-C to copy. I'm going to go back to my word processing program and cross my fingers, Control-V. Oh, pasted it in. There you go. Eureka. It actually worked. Okay. Let me see what it says here. Paste special. See, bitmap. It's showing me that I can paste it in as a picture. In fact, it is a picture in the, although it is a picture in SPSS, but it's an editable picture. So in other words, I could go in here, double click on it, and it'll open up in another window. And that other window will allow me to do all sorts of things with this, including change colors, highlight things. For instance, I can go in here and make this bold, or change the color of that text. Okay, I think, did it change? No, of course not. Of course not. Maybe we got to highlight. Okay. Apply. No, not cooperating with me today. But you guys can play around with it and get it to work. Okay, I don't want to kill too much time with this. Okay, and once you put it back into the output sheet, it'll return to whatever it needs to be. Okay, I'm not going to save that. You know, I'm sorry I didn't. Let me do this again. Analyze. Let me do a quick thing here. Okay. I just wanted to get in, I closed the output window. I wanted to get a new output window. One of the ways you can get this data out of here is to copy it into a word processing or page layout program, right? Which is probably what you're going to want to do most of the time, because you're not going to want all that other detritus that you don't need. If you're doing a report, what do they call when you guys do a thesis? They call it a capstone, right? If you're doing a capstone, you want to display statistics. You want something that will explain some of your work and so on and so forth. You don't need all that other junk. You want that table in there so they can understand your summary of that information. You want that graph in there so they can see it visually. So in this case, I would just copy and paste that into that document. On the other hand, you might want to give someone all of this information to show them what you've done, the progress that you've made and what you did first. And you may want to save it for yourself later on in a format that you could edit in a Word, editing doc, in a Word doc, in Word or some other word processing program. If you go up to File, File, and you say Save As on the output window now, one of the options that you have, it's not there. File, let's see, File, case outline, edit. Save case special, copy as, where is it? Go to case, where's export? Oh, there it is. I'm in the wrong side. I was in edit. Go up to file and say save as. Yep, I'm still in the same thing. Try it again. File, export as a web report, or you can go down to export again. And in export, you can tell it to save it as a variety of other kinds of files, text files, portable PDF files, so on and so forth. But one of the things you might be most interested in is saving it as an RTF file. That's called a rich text file. That's basically the same format that Word does. Okay, so in other words, you could save this whole thing. You have to go down here and give it a name. Right now, it's called output.file. I know a lot of you guys upload the file as the, I know you're doing that, trimming it down after you export it like this, because you leave the name output on it. I'm going to put test. I'm going to change that to test, and you can go navigate to wherever you want to go. Desktop, for instance, say OK, and it saves that whole document as a Word file, right? So you have the whole thing there later on if you're interested in it. I ask you to, on the assignment, some of you that uploaded a .spv file, the output file, or a .sav file, the SPS. I told you, well, yeah, that's nice, it's right, but come back again later for more points because I need you to upload it as a Word document. Why am I doing that? Because when you're presenting this information, you're going to be giving it to people that may not have SPSS. They may not have a version that can open that file, and so on and so forth. So if you're expecting someone to use the information that you're transmitting usefully, you need to put it into a format that they're going to be able to gain access to. So for the most part, that's usually going to be a Word document. Okay, so that's why I'm insistent on that, not because, I'm being mean. Or maybe I am being mean. That also. Let me close this. Okay, why am I doing this? Close. Yes. I want to proceed. Save changes. No. Okay, good. Expired. Okay. So now let me go back to Blackboard here. Okay.
Next, we will move on to basic study designs and something.
This is Professor Weicker. How many of you guys know Professor Weicker? She used to teach us in the School of Public Health. Any you guys remember her? No, I guess so. You guys are all too new to these things. Okay, I'm gonna play this. It's 19 minutes long. It's an introduction to study design. Okay, so I'm gonna play this. You guys want to take a quick break? I'm gonna take 2 breaks now, and again in about an hour or so. So let's take a break. Come back. I'm gonna start this playing for 19 minutes, and then we're gonna move on to new material. We'll take another break at that point then. Okay, so fast one, 5-minute break. Rather than 1 10-minute break, take a 5-minute break. And I'll get this set up in the meantime. So you guys online, this link is on Blackboard. You just saw it as a matter of fact. This link is there on Blackboard. Let me pull this up so I can see this. Okay, this link is on Moijin, why do you have a question mark there? What does that mean? Is that a question? Now you have an exclamation point. It's an important question. I need more than that. What I'm going to ask you guys to do is go to Blackboard. I'm going to pause the recording and the broadcast. And I'm going to, in this class, I'm going to play this video. I'm going to start in a couple of minutes. I'm going to play this video. And while this is, I'm going to play it off the PC that's here in the room because it's going to work better. But I'm going to pause the recording and I'm going to pause the broadcast so that you guys at home can, on your own computers, play that video at the same time. You're live. You are live. That is correct. Okay, so why don't you guys do that and come back in about 20 minutes and we'll be back online.
This conference will now be recorded.
Oh, goodness. Okay. Do that. That's my screen again. Yeah, sure is. And let me load that screen up. Right. Okay. So you guys online, hopefully you guys can see me there, right? So you guys online should be able to see and hear me again. If you want to check your live status again, you can type it in the chat box. That'll help. So I know you guys can hear me. And but I'm going to continue. The video we just watched described different kinds of strategies for sampling, study design, and so on and so forth. It's really important because you're going to put a lot of resources, money, time into gathering data and performing a study. You guys that are eventually going to be looking at doing a capstone or a project of some kind. It may involve doing designing your own study. It may involve collecting your own data and so on and so forth. It's really incumbent on you to kind of plan how are you going to collect the data, what your study design is going to be, so that you don't wind up painting yourself into a corner. I get a lot of people coming back a couple of years after they took biostatistics, saying, Professor DeVito, can you help me analyze the data that I've collected, right? And I look at the data they've collected, and I can think of a dozen ways they could have done that might have been more interesting, better, more efficient, a little bit easier to analyze, and so on and so forth. So that the time to think about how you're going to analyze and present your data is before you do the study, not after you collect the data. It's nice to be able to say, well, I'm going to do a survey. I'm going to collect this information. And, I'll just get the data and then I'll worry about what I'm going to do with it later on. But that's the last thing you want to do. You want to understand study design. You want to understand sampling, what kind of sampling mechanism you want to use, and so on. So really help you out. So this is not going to be on one of the exams or anything like that, but I will bring it up after we reach kind of a little bit after the middle of the semester, because as I started to mention, you guys that are nutrition students, you're going to have two exams, exam 1, exam 2, they're on the syllabus on the calendar. And at the end of the semester, instead of a third exam, you're going to have a project. And that project is not going to be a capstone. It's going to be a relatively simple project. It's going to be the preparation of a poster session, right? The poster is a way that a person would present their research at, say, a conference or something like that. They do a poster, and they put up on that poster the title of their research, who they are. They put on there a description of what their objective was. They present some descriptive statistics. They then say how they gathered data, what the methodology was. Then they put their results and they put their discussion and conclusions. And these posters are lined up, could be hundreds of them, at American Public Health Association conference is coming up, I think, mid-October sometime, second week or third week of October. And people will go down to Washington, they'll go to the American Public Health Association conference, check it out online. They'll go down there and there'll be probably 40, 50 people presenting papers at a podium to an auditorium, to a group of people in a room, and so on and so forth. But there are going to be many other people that are doing research in public health that are not going to have that opportunity. So they'll create a poster, and these posters would be lined up in a hall somewhere, in rows. And people attending the conference will walk down those rows and they'll look at that. Oh, that's interesting. That's okay. And here's somebody that's doing something I'm really interested in. And, I need to know something about that. They'll stop there. They'll talk to the person that is standing there that is presenting the results of their, or the progress on their study. And they can ask them questions about it. They can ask them what else they're doing. They can trade information and so on and so forth. So you're going to do a simple. It's going to be really, if you can imagine something that you could do in large text, large enough to be able to read from a few feet away, maybe anywhere from 6 to 9 PowerPoint pages, right? Description, descriptive statistics, conclusion, so on and so forth. I'll have a format for you there. I'll have a format I'll post, well in advance. And I will give you data sets that you can work with, or you can bring your own data sets if you want to. If you're doing something in another course, if you're doing something at work where you have data that you can work with. And you'll be asked to use some of what you learned here in terms of the statistical methods to maybe only one test, maybe a couple of tests, what you learned about displaying descriptive statistics, even some stuff we've done already with charts and tables, to create that poster, right? And then, best of all, you'll each have 5 minutes on the last day of the class to present it verbally. You'll stand next to it and describe your presentation to you. I see a lot of smiling faces out there, right? Everybody likes that idea. Now, for you people that are not nutrition students, since some of you are not required to actually attend in person, you will have the option of doing the poster presentation or taking the third exam. So for those people, nutrition guys have to do the projects, your brick and mortar people. The other guy's going to have that option. Trust me, the project is going to be way more interesting than taking the exam, because to be honest with you, the last parts of you're going to be talking regression and logistic regression a little bit, and linear regression. The last part of it gets a little challenging and stuff like that. So I want you to learn it, but it might be a little easier to apply it than to, have to answer a lot of questions about it and stuff like that. Right. So I think you're gonna prefer, in the long run, you're gonna prefer the idea of doing the project. Any questions so far about that? Okay, nobody's concerned about that. They're okay. Anybody have any? If you have any personal issues with presenting or something like that, you can communicate with me privately, and I'll find a way to get around that. Okay, so I don't want to. I'm not pressuring. I don't want to pressure you into something that's going to be difficult for you to do. On the other hand, I think this is a great way for you to really kind of cement your knowledge in this course, is to really apply it yourself. Okay, like I said, I'll provide data that you'll be able to use, provide other data sources. You can go out and find data, you can extract data from. And again, if you have your own data you want to bring to the table from another course, or combine this work with something you do in another course, then that's perfectly okay too. As we get to the middle of the semester, I'll have landmarks for when parts of it are needed. So for instance, the first thing is going to be a description of what data set you want to work with, and generally what you want to demonstrate, so that I can review it before you put too much time in, so you don't paint yourself into a corner. Okay, so let's move on to the next thing that we're going to be interested in here, and that's we're going to start talking about probability. And probability, then we're going to move on, after we talk about probability, we're going to move on to diagnostic tests to end the day. And one of the elements that comes up in the diagnostic test is this idea of conditional probability. And we'll talk about that because it's important in diagnostic testing. So I'm going to open up this first document, which is probability exercise 1. Okay, let me find my folder. Wherever it is, here it is. And you guys have that on Blackboard if you want to open it as well. Or you can just look at, follow what I'm doing here. Okay, so first of all, as far as probability is concerned, first thing I want to talk about is this idea of mutually independent and mutually exclusive. Okay, so when we have a couple of events that occur, if they're independent, I'm basically saying that the outcome in one instance does not affect the outcome in the next instance. So for instance, if I flip a coin, I have a 50-50 chance of getting heads or tails, right? If I flip that coin again, I might have a 50-50 chance of getting heads or tails. So let's say I flip that coin 10 times and I get heads every time. What's the probability of getting heads or tails on the 11th flip? It's maybe 50%. They're independent events. The coin does not know that heads came up 10 times in a row. Now, if you're a gambler and you have that mindset, you have all sorts of machinations going on. Well, it's on a run. It's going to do this. It's due. Tails are due. You've probably heard a lot of sports fans that they're due for a win, right? Because they're terrible and they've lost so many, so they're due for a win, even though it's just as likely they're going to lose again, right? So you've heard that, but there's that idea of independence. So most of you are looking at things that are independent events for right now. There's the other idea, which is whether an event is exclusive or not. In other words, could there be two outcomes at the same time? Most of the stuff we're going to look at is going to be mutually exclusive. In other words, coin flip. It's either heads or tails. Right? Can't be both heads or tails. Can't be anything else. Gender, male or female. And diabetic, for instance, either diabetic or not diabetic. Okay, so you're smiling when I say that about gender. I know I'm old and I'm not used to adjusting my thinking here. I understand that things are more complicated these days. Actually, they've always been more complicated. Just nobody would acknowledge they were more complicated back when I was younger. So at any rate, so bad choice. I won't use gender anymore. I'll use something else. Okay, so let's take a look at probability. Let's say that the probability of an individual in a population being insured is 80%, right? If you choose one person randomly from that population, what's the probability they're insured? Well, it's 80%. Yeah, it's 80%, same thing. Let's say you choose 3 people randomly from that population. What's the probability all 3 are insured? Let's think about coin flip first. What's the probability that you would get a heads when you flip a coin? It's 50%. 1 out of 2. What's the probability if you flip a second coin? It's also 1 out of 2. Probably you get a third. What's the probability that you get 2 heads in a row? Well, it's a 50-50 chance you get the first heads, 50-50 chance you get the second head. So it's 0.5 times 0.5. So it's 1 in 4. It's 0.25. So there's 1 in 2 chances of getting one head, 1 in 2 chances of getting two heads. For them to occur together, then that's 1 in 4. For 3 heads in a row, it would be 1 over 2 times 1 over 2 times 1 over 2. 0.5 times 0.5 times 0.5, which is 0.125, which is 1/8. Right? So 1/2 times 1/2 times 1/2. You can look at it that way also. So we just multiply that, right? So the probability that that all 3 persons would be insured is 0.8 times 0.8. Excellent, great. Okay, let's say that you randomly choose 10 people from the population. What's the probability that all 10 are insured? 0.8 times 0.8 times 0.8 times 0.8 times 0.8, right? 10 to the 0.8 to the 10th power, right? Multiply out 10 times. Fine. What's the probability? What's the probability that if you choose 3 people randomly from the population, none of them are insured? None of the 3 are insured. Bingo. 0.2 times point. Exactly right. 0.2 times 0.2 times 0.2. Okay, that's pretty clear, right? Because the probability of being insured is 80%. So the probability of any individual not being insured is 20%. They're mutually exclusive. You're either insured or you're not insured. So if it's 80% is insured, 20% is not insured, right? So it'll be 0.2 times 0.2 times 0.2. Now, what if you repeat your sample of 3 people? Remember 3 people that were 80% of them were insured. What if you take that and you repeat your sample of 3 people 1,000 times, and you find that 75% of the time all 3 are insured? What does it tell you about this? You took it a lot of times. You took 3 people, and you found 75% of the time found all 3 people were insured. What did you expect to be the outcome? You expected the outcome on any individual sample. You expected the outcome to be 0.8 times 0.8 times 0.8. You expected that about 50% of the time you would find those 3 people to be insured. If you do this 1,000 times and look at the average that you got, sometimes you'll get 2 out of 3, sometimes you get 3 out of 3, sometimes you get so on and so forth, right? It's gonna vary, but your expectation is over long term, you would see this outcome, 3 out of 3 insured 50% of the time. What if you actually do it and find that 75% of the time all 3 are insured? What does that tell you about your initial assumption? They're not independent, right? Why might they not be independent? Well, let's say the way you did your random sample is you just took the next 3 people that walked up the street, then you waited 20 seconds, you took the next 3, and so on and so forth. Well, people that are walking in a group might be all insured together. If they're a family and one of them insured, chances are that the whole family's insured, right? Maybe they're coworkers and they all work for the same company and they're all insured. So that would suggest that if you don't get the expected outcome, which would be 50% of the time that we would expect to see all 3 people insured, and it winds up being different than 50%, significantly different than 50%, you would start to think about perhaps my assumption about my sample being independent or its outcome being independent is not true. Right? So if that comes up on an exam and you see something like that, maybe you should say to yourself, "Oh, let me check that. Does that look right?" Okay. So all right. So that's an interesting way to start. That's pretty simple. Let's move on to this idea of probability trees. Now, I mentioned to you this idea of flipping a coin. If we flip a coin 3 times, the probability that we would get all 3 heads is 0.125, 1 out of 8, right? All 3 coins would be heads. What's the probability you get all tails? It's also going to be 0.125, right? Same, 1.5 times 0.5 times 0.5. Okay, now what's the probability that you would get 2 heads and 1 tail? What's the probability you get 1 head and 2 tails? Well, wait a second. There's a lot of possibilities here. Let's take this idea of 2 heads. How many ways could that happen? You could get heads, heads, tails. You could get head, tails, heads. You could get tails, heads, heads. There's at least 3 ways that can happen. It's no longer an exclusive event, right? So it gets complicated now, right? This idea of it's very simple if we were just looking at all of them being heads, all of them being tails, all of them being diabetic, all of them being not diabetic. If we start to consider what's the probability of something in between, things can get a bit complicated. So one of the ways that we could examine that is by plugging this in and creating a probability tree and looking at all of the individual possible outcomes. Okay, so let's give this a try. So I'm going to start with the idea of my coin flip. And my first coin, here's my first coin. My first coin can either be heads or it can be tails, right? Okay, so I flip it. If it comes up heads, my next coin might be heads or it might be tails. If it had come up tails, the second coin could be heads or it could be tails. So now when I flip my third coin, well, I already had each one of these are possibilities. So it could have been heads, heads, heads. And my next coin could be either heads again or tails. And if it had been heads, tails, well, then the next coin would have the same possibilities, heads or tails. And again, with the last one, heads or tails, right? So these are 3 coin flips, right? 1, 2, 3 coin flips. So let's take a look at these different possibilities. So heads, 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 the probability on each one of these, 0.5 times 0.5 times 0.5, this is 0.125. What's the probability of getting heads, heads, tails? Well, 0.5 times 0.5 times 0.5 is 0.125. And 0.5 times 0.5, this is 0.125. And this is 0.125. And this is 0.125. And this is 0.125. And this is all of the possibilities that we have for 3 coin flips, right? Heads, 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 tails, and so on and so forth. All the different possibilities that you can have. What do you think this is going to add up to? If you look at all the possibilities added up, all the probabilities added up to together, right? There's 8 of them, right? So I got that right? Is there 8? 1, 2, 3, 4, 5, 6. I missed a couple here. Okay. Da, da, da. Oh, here, heads and tails. I missed this one down here. Okay, heads. I missed this one down here. Heads, tails, all 3 tails. 0.125. 0.125. Right, there's 8 of them. Well, 8 times 1/8 is equal to 1, right? That's all the possibilities there, right? They're all equally likely. Right? As it happens in this example, they're all equally likely. Well, let's examine that. What's the probability you get 3 heads? Well, it's going to be 0.125, exactly what we predicted before. What's the probability you get 3 tails? 0.125, because there's only one way out of 8 possible ways for that to occur, equally likely ways to occur. What's the probability you would get 2 heads? Let's take a look at this. 0.5, okay, so this is 2 heads. This gives us 2 heads. Put a star next to that. How about this? Heads, tails, heads. That gives us 2 heads. Well, how about tails, heads, heads? That gives us 2 heads. All the others don't give us 2 heads. They give us only 1 head or no head. Okay, so I put those 2 together, and I put those 3 together, and what I get? 0.375. Right? And what's the probability that I would get only 1 head, 2 tails, in other words? Well, again, it's 0.125 plus 0.125 plus 0.125. That's 0.375. So the probability of getting 2 heads is 0.375. 2 out of 3 coins coming up heads. Probability of 1 head out of 3 coins is 0.375. Probability of none is 0.125. Probability of all 3 is 0.125. Again, it all adds up to 1. Pretty simple. Now, what if I ask you, what's the probability of getting 4 heads out of, what's the probability of getting 8 heads out of 20 coins? Well, I don't have enough paper to do that this way, right? I mean, I'm going to wind up by that bulletin board over here by the other computers. We need another mechanism for figuring that out, to figure out these odds. Okay, now before I do that, I also want to mention that there's another way you could look at this also, and that is, if you look at this, I'm not going to bother to draw this. Okay, in this one, they look at the possibility that that a student's taking a multiple choice exam, 5 choices, right? And 3 questions. And I know you've never been in this position, right, on a multiple choice exam, but they have no clue which of the 5 answers is correct, right? That, I know that's never happened to you, right? So if they had no clue which answer was correct, well, the probability of getting any of these questions correct is 0.2, right? 20%, right? 80% chance of getting wrong, 20% chance of getting right. Okay, so you could set up the same kind of tree, except this time the probability of getting the first answer correct is 20%. Getting it wrong is 80% incorrect, incorrect. And then if they got the first one right, then probably getting the second one right is 20%. Getting it wrong is 80%, and so on and so forth. Again, if you got the first one incorrect, then that's probability of the second question. They're all independent events because they're clueless completely, and one question's not related to the other. And then eventually, in this case, the probability of getting all 3 correct is like under 1%. Probability of getting all 3 wrong is about 50%. And then we have all the other possibilities in between. So this is working the same way, even though it's not 50%. The probability, if you look at it from the correct perspective, the probability of success, getting it right, is, and I'm using that term because I'm going to use it later on, probability of success, getting it right, is 20%, right? So it's the same kind of outcome, but the numbers are different because the probability of success is different. It's not 50% anymore. Okay, so I'm not going to worry about for right now what the results of this is. Okay, so I'm going to move on from there. We're going to keep that in the back of our heads. The idea here is that probability to get them all correct, they're all successes or all failures, is easy. Just multiply them out. Probability that there's a combination of success and failure gets complicated because there's many ways you could get that kind of outcome. So I'm going to move on to 3. Okay, so here's a table. Sometimes we call this a cross tab. Sometimes we call it a contingency table. But it's a table of rows and columns. And in the rows, we have gender. And in the columns, we have marital status. And there's a total at the end, make things complete. Total at the bottom for each vertical column, and there's a total at the end for each horizontal column, and there's an overall total. It represents the marital status of U.S. population in millions. Okay, we can just work with these numbers because we're going to be looking at probabilities. Okay, if one person is randomly selected from the population, what's the probability that person is divorced? Anyone give me the numbers there? One person is randomly sampled from this population. It's probability that they're divorced. How many people in this population are divorced? Right, divided by 214, right? Because we're talking about the whole population, all the divorced people and the total population, right? So that's about 10%, right? Looks like roughly. What's the probability that a person is male in this population? Where am I going to find that information? Let's see. Yeah, we're looking over here, and then we got the totals for male and female. So the probability that they're male is 104 over 214. Okay. Find the probability that person is both a male and a widower. What's the probability you randomly select a person from this population? Yes. Oh, no, they're kind of separate questions. Okay, let's answer your question. Let's say that second question, what's the probability is male and divorced? You tell me, what's the probability that person is both male and divorced? Okay, it's still 14 because we're looking at the whole population, right? But now they have to be male and they have to be divorced, so it's only 9 over 214. Okay? So I'm going to go back to our original thing. What's the probability that's just that they're male? And that's going to be, let's see, there's 104 males, 104 million males over 214, right? The total population. Okay, what's the probability a person is both male and a widower? Randomly select a person in this population. Well, male, widower, 2.7 over 214, it's a little over 1%, probability that we would randomly select that person. Now we're going to get to the point that you started to hit on there, which is important. Given that the person is male, what's the probability that he's married? There's a special name for that. That's called a conditional probability. Given that the condition the person is male is satisfied, starting with that, what's the probability that he's married? Okay, well, first of all, since we're saying that he's male, now we're only looking at 105 million people. What's the probability that, given that he's male, that he's married? Well, there's 63.5 million males that are married out of 104.5 million males. So it's about 60% or so, right? That's a conditional probability. And you started to point that out right there. You kind of had the right instincts on this. Okay, so you might see a table like this on the test, ask you a few questions about it, including interpreting some, whether, a conditional probability or two. Let me do one more. Given that a person is a widower, what's the probability that they're female? Well, now, once we say given that they're a widower, we're only dealing with that column, that group. So given that they're a widower, what's the probability they're female? Well, it's 11.3 over 14, right? No, that's only if you don't have that condition, right? In other words, if you said, what's the probability that a person is female and widowed in this population? That would be 11.3 over 214, right? But given that they're a widower, given that they're widowed, what's the probability that they're male? In other words, once you have that condition, they have to be only looking at the people that are widows. So given that they're a widow, what's the probability that they're also female? Well, that's 11.3 out of 14. Okay, I don't want to say anything because there's only one other male in this class, but this is not good news for us. You see those numbers there, right? Okay, so let me close that one. Let's move on. Okay, on that note, okay, so now I'm going to go on to this idea of diagnostic tests. Okay, so anybody here have a nickel allergy that they want to admit to? I bring that up because I think I'm pretty sure I'm allergic to nickel. And I think I know that because whenever I wear I see I'm not wearing a watch, right? Whenever I try and wear a watch, the stainless steel back gives me a rash. And stainless steel is an alloy. It's got steel in it. It's got nickel. It's got cadmium. It's got its whole range. Depending on what there's a million different grades of stainless steel. Depending on what grade it is, has different quantities of these different things. But it almost always has iron, chromium, nickel, and a couple other metals in it as well. Right? So it almost always has some nickel in it. So I get a rash, and the most likely material that's in there, remember, even when you perspire, even though it's stainless, it does dissolve to some degree. It does corrode slightly. I had a friend that worked for U.S. Steel, and when they had customers, you ever buy something that's made out of stainless steel, but then you start to notice maybe it's a grill or something like that, you start to notice rust on it and stuff like that. I used to say to him, I think I had one at the time, I said to him, this thing's rusting. He says, well, I'm just going to tell you the same thing we tell our customers. I said, then what's that? He said, it's stainless steel, not stain-free steel. So at any rate, the next time you buy a stainless steel grill, keep that in mind. It's stainless, not stain-free. So at any rate, so I think I'm allergic to nickel. I think it's a much more common allergy than it used to be because a lot of people get steel piercings and stuff like that nowadays, and I think it's becoming more common. Okay, so let's take a look at this. Now, typically you go to an allergist. How does he test whether or not you're allergic to something? He does a challenge test, right? They used to call them patch tests or something like that. Well, no, that's TB. They used to call it patch tests. What do they call that test where they put a grid on your arm or something like that and then poke you with stuff? It's a challenge test. It challenges your body to see if you get a reaction, which is bad in a couple of ways because you could get a nasty reaction, right? You could get more of a reaction than you want to on a test like that, right? So that's a little slightly invasive. Nobody's ever had that test done? Nobody at all? Okay, so at any rate, that's what they do. They put a grid on there and they poke you with stuff like pollen or dog hair. I don't know, whatever. They don't actually. I'm sure it's not actual dog hair, but some compound that would represent dog hair, right? Or cat hair, right? So you can tell if you're allergic to mold, cat hair, and so on and so forth. It's a little invasive. Let's say that a pharmaceutical manufacturing company comes up with a non-invasive test for determining whether or not you're allergic to nickel, and they want to market this test, but they want to test this. So they take a sample group of 100 subjects who are known to be sensitive to nickel, right? They know that those people from previous experience, because they've been diagnosed before, they're known to be allergic to nickel, and they use this diagnostic test on them. And out of the 100 people, it gets 80 of them right. It's a test positive for 80 of those 100 people test positive, right? So 80 out of 100 people were correctly diagnosed, were true positives for nickel allergy using this screening test, okay? And that 80%, 80 out of 100, is called the sensitivity of that test. The sensitivity is how good that test is in identifying people that have that condition. Okay, so now that begs the question now, but what about people that don't have the test? Maybe it's just 80% of the time it says everybody has the nickel allergy. Well, let's take a look at how that works. They would take another control group of 100 subjects that are not sensitive to nickel. They've gone through other testing and they've been screened with a gold standard test of some kind that we're sure they're not sensitive to nickel, and they give them that diagnostic test. Turns out 90 out of 100 times it correctly identifies them as true negatives. They don't have the allergy. It says no, they don't have the allergy. 10 times it says that they're positive for the test. Gets it wrong. That's called a false positive, right? Because they tested positive and that was wrong. Well, that 90 over 100, that's called the specificity. So, long story short, the sensitivity is how good the test is at predicting that people that have the disease or condition actually test positive with that test. And the specificity is the probability that someone that doesn't have the disease would test negative, correctly test negative for that test. So in this particular test, the sensitivity is 80% and the specificity is 90%. Okay? Now, let's say that we have a population, and in this population, I'm going to take a population of 1,000 people. The prevalence of this particular condition, nickel allergy, in this population is 20%. Clearly, in our population, it's not 20% because it looks like I'm the only one here that will admit to perhaps. I'm not sure. I've never gone to an allergist. I just stopped wearing watches. It seemed cheaper and easier. And now you got phones. How many people wish to wear watches? How many guys are wearing watches right now? There you go. You got 1, 2, 3. Is it a fashion decision, or it's because you like wearing watches? Anybody want to hazard a both? Okay, good. All right, yeah. Well, I'm a bit of an engineer, and I'm not, believe it or not, I'm not really a biostatistician. I've been doing this for 20 years. These are course for 20 years, but I'm not a biostatistician by profession. But I can understand that because from an engineering perspective, watches are fascinating. The history of watches is unbelievably fascinating. Anybody ever read a book called Longitude? No. It's very easy to know what your latitude is if you're on a ship, because you can see where the North Star is, what the angle to the horizon and the North Star or the sun is, and so on and so forth. It's almost impossible to tell what longitude you're at as you move across. So if you're Columbus, you got a problem, right? If you're Magellan, you got a problem. There was an award of £1 million that was promised by some scientific group in England for the first person to develop a system that ships at sea would be able to tell what their longitude was. And the only way you could do that astronomically, but you had to know the time precisely, right? So the only way to know the time precisely is to have a device where you can set it and know the time exactly and then take it with you. So there was a race to develop a chronometer, a clock of some kind that you could use on a rocking boat. Remember, these early ones were all pendulums and mechanisms that if they moved around would not keep time well, and so on and so forth. That would lose time, gain time. They were reliable. So there was a cold weather, warm weather. They would run differently as the metal expanded and contracted. So they weren't reliable enough to predict longitude. So there was £1,000,000 reward. There's a book written about the quest for finding a mechanism for doing that, which was really fun, developing a clock that was accurate enough that you could take on a ship and do that. So why did I get off on that tangent? So we talked about watches. So here, let me go back to biostatistics again. So I know what that prevalence. I started talking about prevalence. And I asked about how many people were in watches. So at any rate, getting back to this, prevalence of this disease in this population is 20%. I'm making up that 20%. So I'm going to open up. There's an Excel file. I'm going to put this aside. I'm going to open up an Excel file which is associated with this, which is a blank cross tabs. I'm going to open this thing up. Okay, so disease plus means you got nickel allergy. Disease negative means you don't have a nickel allergy. T plus means you are tested positive. T minus means you tested negative. So if my population is 1,000, right, and my prevalence is, then this is this is not the study. The study was done to figure out what the sensitivity and specificity was. In fact, I'll write that over here. I need to check what's going on online for a second. Okay, you guys just, I don't, not a lot of comment from the peanut gallery online. Yeah. Anybody know where the expression peanut gallery comes from? From Howdy Doody, a kid's show in the 50s. We used to have an audience of about 50 kids that would be in a little area over there. They used to call it the peanut gallery. Okay, prevalence. So I'm gonna mention here in this test, we previously decided that the sensitivity of this test was 80%. The specificity of this test was 90%. And the prevalence of this condition in the population was 20%. I'll put 0.20. Okay. So let's build this table up from there. Can you see the whole thing behind me? Yes, you can. Okay. So if we have 1,000 people, we randomly select from this population with a prevalence of 1,000, a prevalence of 20%. How many people out of those 1,000 actually have the disease? Out of 1,000. Right? You'd expect 200 of them have the disease, right? 20% of 1,000. Okay. That number down here is the total people that have the disease in this random sample of 1,000 people in this population. How many people don't have the disease? 800, right? It seems fair enough, right? So now 200 people have this disease. How many of them would you expect, given this screening test, to test positive? We would expect 80% of it. 80% of the time we get that right, that diagnosis right. I'm going to put something in here first. True positives, true negatives. Okay, what's this? That's false. What did they test, positive or negative? They tested negative. Those are false negatives, right? Right? Well, look at what the test is. Test is negative. So there are people that had the disease, they tested negative. So that's a false negative. How about up here? Good, false positives. You're catching on, right? False positives, right? Because they tested positive, but they don't have the disease, right? Okay, so I'm going to replace this with numbers now. So how many true positives did we have out of the 200 true positive tests? We have 80% of the time. So we have 160 people that tested positive. How many false negatives do we have? 40, bingo. Okay, now out of the 800, our specificity is 90%. So that means 90% of the time we get it wrong on people that don't, we get it right on people that don't have the disease. So how many true negatives do we have? 90% times 80, 800 is 720, right? Actually, it's easier to do the false. And now false positives, these are people that it got wrong 10% of the time it got wrong. So that makes sense that it would be 80. Okay, you all in agreement on that? That makes sense? Okay, so I'm going to go across here and I'm going to take a look at how many people tested positive. We had 240 people tested positive. We had, how many people tested negative? We had 760 people tested negative. Does that add up to 1,000? Sure it does. Okay, so now I'm going to look at, the next thing I want to look at is, let's take a closer look at these 240 people that tested positive. How many of them actually had the disease? 160. 80 of them didn't have the disease, even though they tested positive. So the presumption is that they need to go on for further screening, treatment, so on and so forth. Could get expensive, so that's not a good thing, right? So let's take a look at something we call the positive predictive value. Out of the 240 people that tested positive, how many of them had the disease again? Well, that's 160 out of 240. So if you are an individual in this group that tested positive, what's the likelihood you actually have the disease? 67% is the probability you have the disease. That's the positive predictive value. What's the negative predictive value? Who wants to tell me what that is? Okay, that's the probability that you don't have the disease given that you tested negative. Right? What is that? What's that going to be? How many people tested negative? 760. How many people are really negative? 720. So the negative predictive value is 720 divided by 760. You guys comfortable with that? So you, sure. I'll do that again. Okay. Yeah, negative predictive value is a little bit more confusing, isn't it? Oops. Okay. So negative predictive value is how, if you tested negative, what's the probability that you don't have the disease? It's a probability that's correct, in other words. So 760 people tested negative. 40 of them had the disease. 720 of them didn't have the disease. So how good is this at predicting that you don't have the disease? Well, that's equal to the number of people that tested negative that don't have the disease that are correctly identified over the total number of people that tested negative. And I'll hit enter. Okay. 95% of the time, you got a negative test means you don't have the disease. 5% of the time, you got missed. Right? So on and so forth. They thought you had the disease and so on. Okay, so I'm gonna put this in another format here. In the future, you might help out. So the positive predictive value is equal to the true positives divided by the true positives plus the false positives. Okay, in other words, everybody that tested positive is on the bottom, and only the true positives are on the top. Oh, oops, I should have put a space in front of there so it doesn't think it's an equation. So, and the true negative is equal to the true negatives divided by the total number of people that tested negative, which is the true negatives plus the false negatives. Right? That's everybody tested negative. The true negatives, the people that really were negative, divided by the total number of people that tested negative. That's your negative predictive value. Okay, so what do you think? Is 67% a pretty good positive predictive value? What do you think? Kind of, yeah, not, you want to know something, it's really not too bad, right? Let's do something interesting now. Let's run this same test on a population that has a nickel sensitivity of only 1%. The prevalence is 1% instead. So if that's the case, I'm going to go down here. If that's the case, I'm going to do the same thing. 1,000 people. Out of those 1,000 people, if the prevalence is 1%, how many people would actually have the disease? 1% of 1,000 is 10. 10, right? 1% of 100 is 1. 1% down 10. Everybody agree with that so far? Okay with that? Okay, so that would mean 990 people don't have the disease out of that random sample of 1,000 people. If the remember, nothing's going to change it. Sensitivity and specificity is going to be the same. The only thing that's going to change is the prevalence, which is going to become 0.01. Instead of 20%, it's 1%. Squeeze that together a little bit. Okay, so out of the 10 people who have the disease, how many of them test positive? Sensitivity is 80%. 80% of the time it's going to be 8 people. Guys, okay with that? How many people are going to test negative that have the disease? 2. You got 2 false negatives. It's going to miss 20% of the. It's going to miss 20% of the people because the sensitivity is only 80%. Out of the people that don't have the disease, what's the probability that you would correctly identify them as not having the disease? You know, I'm going to do this backwards. The specificity is 90%. That means you're going to get it wrong 10% of the time. So it's easier for me to take 10% of that than to take 90% of that. So that comes out to be 10% of that's going to be 99 people. And that leaves 891, right? Am I right? 891 people. Does that add up to? Yes, it does. Add up to 99. Yes. Did I confuse you by doing that? I did, right? Let me do it another way. Okay, so you got 990 people that don't have the disease. Your accuracy at identifying them, in other words, testing negative, you get it right. You get a tested you get a true negative. In other words, you would correctly identify those 990 people. You correctly identify 90% of the time. You correctly identify them, right? So that's going to be equal to 990 times 0.9. So 891 out of those people you would correctly identify as not having the disease. They would test negative. So that means 99, the remaining people, would have to test positive. False positive, because they don't have the disease. Okay? So now, what's the total number of people that test positive? 8 and 99. That's kind of why I prepped you with that table with the male and the female and the divorce, because you kind of like got to get an idea where what these boxes represent. So how many people tested positive? Well, 8 people tested positive that actually have the disease, and 99 that don't have it. So it's equal to, I'm going to use sum. Just makes it easy. To make it easier, I don't have to think. 107 people tested positive. How many people tested negative? That's an easy one. That's 893. And that adds up to 1,000, so it looks right. Sure.
Always refer to those who have the disease and the specificity refer to those who don't have the disease.
Exactly. It's how good is it protecting that people that don't have the disease are correctly identified. Okay, so now I'm going to calculate my positive predictive value and my negative predictive value. I'm going to start with my negative predictive value. And what is that equal to? That's equal to people that it got right, the total number of people that the true negatives, divided by the true negatives plus the true positives, the true negatives plus the false negatives, which is 893. Okay, 99, almost 100% of the time it got it right. 99.8% of the time it got it right. Let's take a look at the positive predictive value, which is the more important one, because that's the one where we're screening people. We want to catch the disease, right? Let's see, that's what that's equal to. That's equal to the number of people that had the disease and tested positive, divided by the total number of people that tested positive, which is the true positives and the false positives. It comes out, it's 7%. What happened here? This test, if you tested positive on this test, there's only a 7% chance you actually have the disease. What happened here? This is literally the same test. 80% sensitivity. What's the only thing that changed here? The prevalence. Look what happened here. The prevalence, because we tested so many people that don't have the disease, even though we didn't get it wrong very often, only 10% of the time, that led to a lot of false positives. That's what affected the positive predictive value. right? Because we had so many people that tested positive out of that because there's just so many of them. There's so many more than there were before, right? So remember before there were 800, now there's 990 people that were testing. Okay, so now that leads to and now we have much fewer people that tested positive because the population of people that have the disease is so small. So the number of people that have the disease and test positive goes down. The number of people who don't have the disease and test positive goes up, right? So even though the specificity and the sensitivity don't change, the prevalence that had this enormous impact on this. Well, gee, what does that mean for diagnostic tests? That means that when we apply a diagnostic test to a population where the prevalence of the disease is low and we apply it universally, what's going to happen? You're going to get a lot of false positives. Anybody give me a diagnostic test where there's a low prevalence of disease in the population, and then, incidence, you could say incidence or prevalence at any given time, right? So, but when you screen the whole population, you get a lot of false positives. What kind of diagnostic tests were they? Female that's over 50 years old. Maybe pap smear, right? They use that pretty universally. They did. I don't know if they do now. Use it pretty universally. What's the prevalence? What's the prevalence of uterine cancer in the population at any given moment? Not very many cases at any given moment, right? Out of the entire population. Very low prevalence, and a test that probably doesn't have a great sensitivity or specificity, right? And what winds up happening? You get a lot of false positives. Mammography, a lot of false positives. But again, you're looking for breast cancer, you're testing a very large population, but only a small percentage of population at that moment has the disease. How about males? Bingo, PSA, prostate specific antigen. You go to the doctor, if you're over 50, if you're over 40 now, they almost automatically do a PSA. It's looking for a specific protein that's associated with prostate cancer. The cutoff, I think, is 4 or something like that. And if you test over 4, that's a presumptive test that means you should do more testing, right? Or that you might suspect prostate cancer. The problem with it is that when you apply it universally, at that age, 40 or 50, only a small percentage of population, male population, has prostate cancer, right? They have other problems, enlarged prostate, benign prostate, so on and so forth, only a small percentage. As you get older, when you're 70, 80 years old, then the probability of prostate cancer goes way up, right? The prevalence goes way up, and that testament something. What happens is you wind up a lot of people that get freaked out by a test like this, and then have to have to go for more invasive testing, spend more money, so on and so forth. Biopsies are a real issue. If you suspect prostate cancer because of a lot of side effects, there's a high probability of side effects from even the biopsies and so on, and other treatments that might be associated with prostate cancer. So you get a lot of these tests, and that's why you hear a lot of resistance to lowering the age or making insurance companies having insurance companies provide mandatory breast cancer screenings for women under 40 or so on and so forth, or provide money for other kinds of screening tests and so on and so forth. Because what happens is that trade-off is a lot of false positives and a lot of issues that go along with interventions that aren't necessary and so on. So that's why there's always kind of a push and pull between organizations that are interested in reducing the number of specific diseases or cancer deaths, and what the medical profession recommends in terms of when to do screening or whether or not to do universal screening and so on. So let's take a 5-minute break again. We're going to come back, and I'm going to ask you, first of all, number one, during the break, anybody that's sitting around here or something like that, I want you to pick out a screening test. It could be PSA, could be any other thing that you can think of, could be a stress test, an EKG, or a nuclear stress test, or an exercise stress test. And Google, what is the sensitivity, specificity, and the positive predictive value? You can abbreviate that PPV, of that test. And when I come back in 5 minutes, you guys tell me what you found in terms of those tests. And then what I'm going to do is I'm going to give you an example and have you work out the specificity, sensitivity, positive predictive value, and so on and so forth. We're going to also do it, find another way to calculate. Okay, so anybody find any interesting tests? Find some information online? Anybody? Yes.
For the PPV test, it says that sensitivity is 0.59.
0.59.
The sensitivity.
Oh, that seems kind of low, right? That seems a little odd.
It says 0.59 to 1. It gave a range. It didn't give a.
Oh, maybe that's a confidence interval that's probably gave you.
No,
Yeah.
That's what it.
Okay.
And then the specificity was 0.95.
0.0, and what was the sensitivity?
0.59.
0.59, about 60% and 95%. Not too much different than our test here, right? Did it give you a positive predictive value?
44.
44%. So for the PSA test, the positive predictive value is 44%, right? Get in the population that they applied it to, which is probably general population of the United States.
Yes.
Yeah. Okay. So if you have a positive PSA test, the value over 4, there's less. It's more likely you don't have cancer than you do have prostate cancer, because only 44% likely that you actually have the disease. That's the positive predictive value. That's what the positive predictive value represents. So most people that test positive on the PSA are going to be wind up being negative. Right? So that's one test. If you checked out a stress test like a resting EKG, probably has a very low predictive value. If you check out a exercise stress test, probably better, and nuclear stress test, probably even better than those others. Okay, so at any rate, so I'm going to give you an example right now. I'm going to close this, and I'm going to reopen it. I'm going to give you an example up here, and I'm going to say we randomly selected 10,000 people, and of those 10,000 people, let's say 500 of them have the disease, say 9,500 of them don't have the disease, and 150 times we got it right, 50 times we got it wrong, and here we got 150, and here we got 8 equal to this minus this, equal to 550 equals sum of these two is equal to sum of these two, and 1,400 times of 10,000. Okay, see the numbers I got up here? I'm going to ask you to tell me, what is the sensitivity of this test? What is the specificity of this test? And what is the positive predictive value for the test? So I want you to let me know what is the sensitivity, the specificity. I'm going to do it down here. Kind of hard to read off in the corner there. I'll end up hiding the table. Sensitivity, specificity, and the positive predictive value. Okay, I'll give you a few minutes to figure that out. And let me check with you guys online. How you guys online doing? Any questions online? Guys keeping up? Okay, good. Thank you. Thanks for the feedback, Fernando. Oh, I did that wrong. That's wrong. True positives. Okay, can I give this a try now? What's the sensitivity? Everyone hazard a guess on that? I kind of gave you a guideline up here if you guys want to look up for a second. The sensitivity is the number of people that the people that test positive out of the total number of people that actually have the disease. Well, how many people actually have the disease? People that have the disease are the sum of the true positives and the false negatives, right? This column represents all the people that have the disease, right? So it includes the true positives and the false negatives. So the sensitivity is equal to the true positives, 450, over the true positives plus the false negative. In other words, 450 over 500. Okay, or 90%. Sensitivity is tested 90%. Okay, what's the specificity of the test? Well, the specificity of the test is the number of people that test negative that actually don't have the disease. So 8,550 people actually test negative, but 9,500 people are in this random sample actually don't have the disease. That's really, that 9,500 is actually the sum of, I'm going to put it down here. This is true positives plus false negatives, and this is true negatives plus false positives, right? right? So, whoops. Actually, I should have clicked in here and put a space in front of it. Okay. So we have, for a specificity, we have 8,550 people out of 9,500 people who don't actually have the disease. 950 were misdiagnosed. So the specificity is 90%. Sensitivity and specificity in this case were the same. So what's the positive predictive value? The positive predictive value is equal to the total positives, true positives, which is 450, divided by the total positives, which is the sum of the true positives and the false positives. In other words, 450 plus 950 is 1,400. And it's 32%. If you take this test positive, chances that you actually have the disease is 32%. And that's with a prevalence of 500. What's the prevalence here? Prevalence is equal to 500 out of 10,000. Out of 10,000, the prevalence is 5% in this population. What would happen to the positive predictive value if I applied this to a population that has a prevalence of 1%? Would the positive predictive value go up or down? Lower prevalence, what's going to happen to the positive predictive value? Right? It's going to go down, right? Because in a smaller population, we're going to get more false positives. So a positive test won't be as predictive as it would be in a population with a larger prevalence. You guys comfortable with that? You get a chance to play this back again, and maybe this might help you out as well. But remember, the idea here was before, what we did was we applied the same test to a population that had a 20% prevalence, and the positive predictive value was like 67%. Then we took the same sensitivity and specificity. We didn't change that, applied it to a population only 1%, and the positive predictive value went down to 7%. In other words, a positive test was a less reliable predictor of actually having the disease. What kind of probability is a positive predictive value? You think, well, what kind of thing do you think it is? Well, it's a conditional probability, right? The positive predictive value is a conditional probability. It's basically the probability that you have the disease, right? Given that they usually use a pipe, a straight up and down line, for given that you test positive. In other words, the positive predictive value is the probability that you actually have the disease given that you've tested positive. So we're only looking at people that tested positive when we're calculating the positive predictive value. Okay? It's a shift. On my computer, it's a shift over the backslash. If you look carefully, it's buried on there somewhere. Sometimes it's over by the escape, under the escape key, and yeah. That's called a pipe command. Right? That's called a pipe. They use that in Unix a lot as a special operator, special thing to do with a file or something like that. Okay. Yes. That's the positive predictive value. It's the probability you really are positive, D positive, given that you tested positive. Okay.
Will you post those results on Blackboard just as a reference?
I'm sorry. I'm going to put the whole thing. The whole video is going to be on. I'm recording all of this. So within a day or two, it'll be on Blackboard, and you'll be able to watch the whole thing all over again.
But even the spreadsheet, we can see.
Oh, that's a good question.
As a reference.
You can use this one as a reference.
No.
Huh? I dropped the other one. I could recreate it. I can do that. Yes. I'll recreate it again so that you'll have those two tables, so that you'll have them again as well. Okay. So apparently you guys are in a hurry. You got a class somewhere else, I guess.